Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture on control systems. So in the previous lecture we've seen a few things. First, we've already seen that how to sketch the transfer function of a given, the Bode plot of a given transfer function. We've also seen how to sort of sketch these Bode plots for different constituent blocks. In a sense, that is what allowed us to draw the overall Bode plot for a transfer function, whether it's the phase plot or the magnitude plot. We've seen how to handle both of those. Apart from that, we also began seeing what the interpretation of certain terms are. For example, what is a resonant peak? We might have heard about this term earlier, but what is it in a sense? That we've seen. We've also seen how using the Bode plot you can evaluate some of these error constants just by looking at this graphical picture, the magnitude plot, right. We've also seen different interpretations of many of these things. So we've also seen a 3D version of the picture, right, and we've also seen why this zeta value is so important in deciding whether there will be a resonant peak at all or not. Yeah. So having seen a number of these interesting features, we shall continue on our journey, although as I said the goal of Bode plot is to create a parallel path towards designing controllers like you had for root locus based methods. We will not go too deep into that. We will rather look at Bode plot as a means of understanding some of these performance metrics. So it could be that your particular user who is telling you what specifications he or she requires in a system is more familiar with these frequency domain terms, right. Does not necessarily mean he or she understands what poles and zeros are, but they might often specify requirements to you in terms of what is called a say a bandwidth, yeah, what is called, let us say, a resonant peak, or suppose for instance a phase margin, a gain margin, yeah, things like these, right. So these are things that a designer might be asked to adhere to. Now how do you translate these requirements in more technical terms? Yeah, for that you need to understand what these terms at least mean. So we will see how when we see things in the light of a Bode plot, a lot of these things start to make sense, a lot of these terms start to make sense, and our ideas become clearer. So the next term that we shall encounter on this path is, we said this so many times in our earlier lectures, and I have promised maybe multiple times that I will explain this when you have idea about a Bode plot. So non-minimum phase system. So far as our understanding goes, here is how we understand non-minimum phase system. System, let me just say a stable system, because that is what we are mostly dealing with in this classical part of this control theory, right. A stable system is said to be minimum phase if all its zeros are in the open left half plane, okay. So you might wonder what is this, I've given a heading of non-minimum phase system, but I'm going about defining what a minimum phase system is. Well, there's a reason behind that. The obvious reason is any stable system having at least 1 0 in the open right half plane is said to be a non-minimum phase system. So, in some sense you see they are complementary, right. If a system is not of minimum phase, it is non-minimum phase. In other words, even if one of the zeros of the system happens to be on the right half plane, then it no longer qualifies as a minimum phase system, then it is called a non-minimum phase system. Now, immediately you might now start to wonder, what is this business about minimum and non-minimum, what is it, right? Why is it called non-minimum phase, why is it called minimum phase? Hang on a sec. Before that, we are going to take a look at something interesting. Now, consider you have a transfer function g1 of s is equal to s minus 1 upon s plus 1, and another transfer function g2 of s is equal to s plus 1 upon s plus 1, which is essentially 1, right. So, it is a constant that way, right. Now, just think about it a moment here, yeah, and what you will realize is that if you think about the magnitude plot of g1 and g2, yeah, what is the magnitude plot of g1? Let us think. So, m omega for g1 is equal to square root of 1 plus omega squared upon square root of 1 plus omega squared is equal to 1, and of course, it is only obvious that m omega of g2 is also 1. So, if someone just gives you this plot, yeah, it could come from this system. Suppose someone has told you that, hey, there is a system which has one pole and one 0, right. The system has one pole and one 0, right, and this is, let us say, 0 dB. Then also gives you this magnitude plot, all right, and asks you the question, can you identify the transfer function for me? Of course, you cannot, right. Even if you know it is a stable system, you see both these g1 and g2 have the same magnitude plot. So, it is not a 1-to-1 mapping. Just by looking at this magnitude plot, you cannot infer whether it is g1 or whether it is g2, right. So, then what do you do? How are we going to address this issue, right? It turns out that in cases such as this, that is the reason why we say that just looking at the magnitude plot does not suffice, we also need the phase plot, yeah. It would be interesting to look at the phase plot of this, but I have one even more interesting example on hand, so probably we will take a look at that particular example rather than this. So, let us say you have this block like 10 of s plus 10 upon s plus 100, and you have 10 of s minus 10, say for instance s minus 10 upon s plus 100. Once again you see this will also have the same magnitude plot, this will also have the same magnitude plot as this, yeah. Again, you can immediately see that it really does not require too much thought, right, because you just pull out this 10 from here, so it is 100, and you pull out this 100 from here, so it is a unit gain. So, essentially not only do you see that these two have the same magnitude plot, even these two transfer functions also have the same magnitude plot as these fellows, because when you do not have any corner frequencies manifested in the magnitude plot, yeah, how are you ever going to sort of, well, not really, this magnitude plot is going to look a little different. So, of course, I have not put 100, so that is what I missed, sorry about that. So, this magnitude plot is going to be a little different. Of course, it is going to start from 0 dB, and then at 10 it is going to rise a bit, and then at 100 it is going to settle down. So, this is also going to have the same characteristics, it is going to go here. So, let us say this is my frequency 10, this is my frequency 100. So, here also you will see that the same thing happens, there are corner frequencies, yeah. So, I had mistakenly thought I had put an s plus 100 and s minus 100, but it is okay. So, yeah, this is it. So, in these two you see again they have the same magnitude plot, 20 log of m omega and 20 log of m omega. Yeah. Now, again they are indiscernible, right, which one is it, which one is which, right. Even if you have this corner frequency here, because of this change of phase here, of course you don't even have the corner frequency, right. So, it could be s minus a, s plus a adjusted by some factor, right, it could be anything. So, all of those transfer functions would have the same thing here, which is why I thought mistakenly this is not s minus a by s plus a, or rather s plus a by s plus a, this is actually 10 and this is 10 times. So, this is essentially the type of transfer function we have already seen this. Where have we seen this? You see, when the pole is to the left of the 0, we say that this is typically what a lead compensator looks like. Yeah, so this is basically what we have termed as a lead compensator. Yeah, we have seen this while carrying out our studies of the root locus design. But this of course is nothing, this is not a lead compensator, this is actually a what is called a non-minimum phase system, and that is where this non-minimum phase, this distinction comes in. And once we look at the phase plots of these two fellows, that is when it will start making sense as to why we call something non-minimum, or what is non-minimum about this second transfer function we have considered. So, let us look at the phase plot here. What is the phase of this going to look like? Now that we are very well aware of how to deal with this sort of system, so let us call this 0 degree, this is 90 degrees, this is minus 90 degrees, yeah, and this is also say 0 degrees, then you have 90 degrees, and then you have minus 90 degrees. Now, recall in root locus studies we had generally taken this with a negative sign, we had pulled out this minus sign and we had only considered 10 minus s, yeah. But here let us say in this case we are not really interested in doing that, because we are just plotting this open loop Bode plot here, right. So, we are not really studying the variation of the closed loop poles with respect to the change of a particular gain like we did for a root locus. So, here if we are given a non-minimum phase transfer function in this fashion, we just go about our business of plotting it, right. Okay. So, you see that the magnitude plot does not change, but what about the phase? So, let us first look at this, which we understand pretty well by now. So, you see the obviously the constant term does not lead to any phase. So, there are two critical points here, one is 10, the other is 100. So, what about this first numerator factor here? You see the numerator factor, let me use the blue ink here, the numerator factor would go on to have 0 phase until this, and then suddenly a phase of plus 90 from here. The denominator factor would also continue to have this 0 until 100, and then suddenly from here there will be a minus 90, yeah. So, if I sketch the overall plot now, up until here everything is 0, yeah, because both the numerator and the denominator factors are 0, but from here to here, yeah, there is this 90 degree contribution from this numerator, yeah. So, it is going to as if rise from here and it is going to carry on like this until at this point this begins to show up, this contribution due to the pole begins to show up. So, it is going to add a minus 90 degree. So, it is again going to bring it back here, yeah. So, this red fellow you see is the approximate phase plot. Of course, if you are desirous of plotting it more aesthetically, you might make those corrections like this, and this is typically how the phase plot would look like, okay, straightforward. However, the moment we turn our attention now to this, things start to become a little more complicated. Maybe not complicated, but it requires a bit of thought. We cannot just say that a pole coming in means it is a minus 90, a 0 coming in means it is plus 90 blindly. We need to analyze a bit. So, what about this phase of this particular fellow, this fellow who is responsible for this being termed as a non-minimum phase system after all? What about this? Let's try to look at this here. So, what is the phase of this fellow? This is tan inverse, you see, omega over minus 10, and I am very particular about where I am putting this minus sign, because this is telling me this is the imaginary part over the real part. So why am I not just pulling out this minus sign here? I am just keeping it with this 10 here, because I want to remember that this negative sign is coming in because of the real part, right. So because of the real part being negative, I have to carry with this negative sign. If I just put this negative before the factor here, then I will not really be able to make out which fellow is negative. It could be negative because the imaginary part is negative, or it could be negative because the real part is negative. Now this is telling me something. Now if I keep increasing omega, you see what happens. At omega is equal to 0, where does this start from? You see, at omega is equal to 0, yeah, or rather very small values of omega, yeah, this is very small positive quantity, the imaginary part is very small positive quantity. So where is such a complex number sitting? It has, so if I draw this on the complex plane, the phasor whose angle or argument is given by this, it is basically a phasor that's probably got a imaginary part which is very small somewhere here. So this is some small value of omega. On the other hand, the real part is minus 10, yeah. So what is the phase of this? The phase of this is almost close to plus 180 degrees, yeah. So therefore you see, now I know the moment I have this non-minimum phase system, instead of starting from 0, yeah, that is the one big difference. Earlier when I had minimum phase system, I know that at initial parts at least, it will always start at 0 degrees, yeah, because why? Because you just make all of this 0, make all of these S's 0, you ultimately end up with a positive quantity. Here you make all of this 0, you ultimately end up with a negative quantity. So it is as if you are starting from this, the negative part of the real axis, right. So therefore you now have to start from this 180 degrees, yeah, and that is one crucial difference. So every time you encounter such a thing like this, you actually start from this 180 degrees, okay. And then of course now you cannot have minus 10 here, so you have 10 here and you have, let us say, 100 here. So what happens at 10 after all, right? Let us try and understand what's happening at each one of these break frequencies. Of course at 100 we know that the second factor, of course let me plot this as before, the second factor I know how it looks like. What color did I use? I used a green color, yeah. So the second factor I know that it will carry on at 0 degrees till 100, the pole, that is this, yeah, and then it contributes a minus 90 degree here, right, yeah. So it contributes a minus 90 degree here. But what about this 0? As S tends to infinity, where does this go, yeah. So that is a very crucially important bit here. You see, as S tends to infinity, as omega tends to infinity, yeah, as omega tends to infinity, where is this fellow after all going? So it starts at this point where it is like 180 degrees, and then you see this is causing a clockwise rotation, no. So clockwise rotation means what? Clockwise rotation means a reduction, and as omega tends to infinity, you see this fellow is proceeding in this direction. This phasor, this particular phasor here is proceeding now in this direction, right, keeping this part fixed. So the angle starts from angle starts from like this 180 degrees, yeah, and then it gradually comes closer and closer to 90 degrees, yeah. So you see that it goes here like this, and for values much greater than 10, yeah, for values much greater than 10, where does this eventually settle to? So it actually settles to, you will see, 90 degrees, right. So therefore now that is a crucial difference. Earlier what did we see here? You see in this factor on the other hand, we had that for this was basically tan inverse omega over 10, right. So you started from 0 and then you increase to 90 degrees. Here you started from 180 and you reduce to 90 degrees because of this this is clockwise rotation, which is a reduction in the phase. So this non-minimum phase 0, the presence of this non-minimum phase 0 is basically causing a reverse direction rotation of the phasor. Yeah, in this case the phasor was rotating in the counterclockwise direction as omega increased due to this factor. But here it is actually going to rotate in the clockwise direction. So basically what happens that way is, what color did I use? Blue. Okay. So here until 10, yeah, you draw the low frequency asymptote, okay, and then you see from there on it starts going in this fashion, okay. So it goes on with this. So this is my blue factor here and this is my green factor here. So you see in some sense, and this insight is very important, what I am now going to say. You see in some sense a normal 0 on the left half plane would cause a phase increase. So we have this intuitive understanding that the presence of a 0 is like a lead compensator, is like an extreme case of a proportional derivative controller, it adds phase, we call it a lead controller for a good reason, right. We have seen why it is called a lead controller. At every potential point on the root locus it adds a positive phase. We will see in here also, you can see that it adds a positive phase, that is also manifested here. So you can also see the justification of this lead compensator name from the Bode plot, from the Bode magnitude phase plot as well, right. So all this we understand. The moment this fellow with a 0 in the right half plane comes in, it kind of spoils our party. All this understanding that we have about lead compensator, the way the phase plot is supposed to look, all of it changes. Now you immediately see that this 0 on the right half plane has a behavior which is somewhat identical to another pole, yeah, because what happens when a pole is present, a stable pole, that is a pole on the left half plane, you see as you go beyond the corner frequency, the high frequency asymptote has a jump discontinuity and in the negative direction, so it causes a phase lag. A non-minimum phase 0 also seems to cause a phase lag. So not only is it acting against, yeah, not only is it acting against you, it's already defected from your team. So there's a team of zeros and a team of poles, yeah. So the zeros are supposed to add phase lead, the poles are supposed to add phase lag, as we understand here in this plot, right. We've also studied this earlier. But now the moment one of those zeros goes from the left half to the right half plane, it sort of not only defects from its team of zeros, so it takes one 0 away from the team of zeros, but it adds one effect of one pole instead. So that way the resultant plot here would look something like this. Let me use the red ink. So initially you see this green factor is contributing 0, the blue factor is contributing 180, so it stays like this, and then suddenly this fellow contributes a little less, it contributes 90 thereafter. So you immediately have a jump here, then it comes to here, this 90, and at this point suddenly this fellow shows up. So you have another jump here and you continue like this. So again, if you are trying to be very aesthetic about this, yeah, you probably need a plot that looks somewhat like this, yeah. Okay. So that could be your potential phase plot for a non-minimum phase system. Immediately you see the difference between the phase plots of the minimum phase and the non-minimum phase system. And now even if their magnitude plots look identical, by looking at this phase plot you will immediately be able to infer which which Bode plot corresponds to which system. Okay, so that is why you need both the magnitude and the phase plot for system identification. Okay, that's the question we discussed earlier. You remember, if we have the Bode plots, can we identify the poles and zeros of the system? That's a reverse question. Yeah, so Bode plots also help us in system identification, but of course you have to be sure that you have both the magnitude and the phase plot. Yeah, otherwise you could have multiple transfer functions, even stable transfer functions, which have the same magnitude plot as we've just seen here. Yeah, one of them being, only one of which is called a minimum phase and the others could be non-minimum phase. So for example, if you have multiple say you have S plus A into S plus B upon S plus C into S plus D into S plus E, and here you have S minus A into S minus B upon S plus C into S plus D into S plus E. Then you might also have had S plus A into S minus B upon S plus C into S plus D into S plus E. You might have also had S minus A, S plus B, S plus C into S plus D into S plus E, where A, B, C, D and E are all greater than 0 and they belong to the set of real numbers. Okay. So, you see all these 4 transfer functions, call this G1, call this G2, call this G3 and call this G4. You see all of these 4 transfer functions, they will give you the identical, they will give you exactly the same magnitude plot, if you draw their Bode plots, that is, right. But it is their phase plot, it is only by looking at their phase plots that you will be able to discern or distinguish one from the other. Enough said. I have still not explained the main point as to why this is a minimum phase and why the rest of them are non-minimum phase. What is minimum or non-minimum about this? Now you look at this plot here. You see how many poles and zeros does this have? This has 1 pole and 1 zero. This also has 1 pole and 1 zero, of course, that is why they have the same magnitude plot. But you see, what is the net change? So this is the important, this is the pertinent question. So the question being asked is, what is the net change in phi omega as omega goes from 0 to infinity? Notice this is a question that we have already asked ourselves while deriving the Routh-Hurwitz criteria. This has been accompanying us for a long time. We in fact had a name for this in our nomenclature, we called it delta theta from 0 to infinity. This is the symbol by which we denoted this. Excuse me. And we saw that for a system with its poles and zeros all on the left half plane, this is going to be nothing but n minus m pi by 2, where n is number of open left half plane poles and m is the number of open left half plane zeros. Okay. So, I am actually concerned about the magnitude of this, I am not really concerned about the sign of this. So, this is the quantity of interest, and it is based on this quantity that only one of these 4 transfer functions is called a minimum phase and the others are all non-minimum phase. Why? Because remember, this condition, this expression is valid only for G1. What about for G2, G3 and G4? Here is where that idea of defection comes in. So, see, to recall again what I mentioned, when you have one of the zeros on the right half plane instead of the left half plane, not only do you have that particular zero behaving like a pole, but it also takes away from the behavior of the zero. In other words, for every left half plane zero, you have a phase lead of pi by 2. For every left half plane pole, you have a phase lag of pi by 2, and therefore, you have the net resultant here n minus m pi by 2. But now suppose there are n poles, m zeros, and r of the m zeros are in the open right half plane. So, it is a non-minimum phase system we are dealing with. Then notice what is the net contribution, the phase lead that is going to happen. Every time you encounter a zero at a break frequency, remember we just raised this phase plot by 90 degrees. We blindly did that. No? But now those number of non-minimum phase zeros are only the ones, the number of minimum phase zeros are the only ones who behave in that fashion. We have seen the moment we have a non-minimum phase zero, it quite the contrary, it behaves like a pole insofar as the phase plot is concerned. So therefore, how many of those zeros actually behave nicely? So how many zeros are there on the left half plane? M minus R OLHP zeros, and R open right half plane zeros. okay. So of course you might ask, what about zeros on the imaginary axis? Now those are tricky situations, right. So you see then that bringing in the notion of the distance, yeah. So if there is a zero on the right, on the imaginary axis, again it's so called a marginally stable system. We don't like such systems because we don't deal with such systems, we want to deal with internally stable systems, but nonetheless you might encounter zeros, right. A zero does not make a system unstable, no. So if you have a zero, now notice what is the distance at that particular point where there is a zero on the imaginary axis, what is the distance of the zero from that point? It's 0, yeah. So what is log of 0? It's minus infinity. So basically what you will then have is some plot like this which basically goes all the way down, right. It's like a sink, yeah. So that sort of a zero is not something we particularly like, okay. So we will rest that question, we will just consider zeros to be either in the open left half plane or in the open right half plane. So now having understood this, therefore you will see that these fellows will only contribute a plus jump of pi by 2. On the other hand, these R zeros, they will now team up with the poles. So they will behave, insofar as the phase is concerned, they will behave like poles. So what is the net phase change then, right, and here is the crucial bit. So now you see the net phase change delta theta as we go from 0 to infinity is now going to be n plus r minus m plus r into pi by 2, that is n minus m pi by 2 plus r pi, yeah. That is exactly the net phase change. Now you see, because r is a positive integer, so because r is a positive integer or at least a non-negative integer, yeah. So it's either 0 or a positive integer. Therefore this, now if you look for all these transfer functions, they all have the same magnitude plot, but their phase plots will be different. So only this fellow will have a net phase change of n minus m pi by 2, which is equal to, in this case, pi by 2. What about this fellow? You see r is 1, yeah. So this is going to be pi by 2 plus r pi, so it is plus pi. So it's going to have a net phase change of 3 pi by 2. Same with this fellow G4 is also going to have pi by 2 plus pi. And what about this fellow? Well, this fellow will have again pi by 2 plus, now you have 2 of these poles, right, so it's 2 pi. So that is going to be the net phase change, right. So you see, among all transfer functions which correspond to the same magnitude plot, the one corresponding to the minimum phase system has a minimum change of phase in going from 0 to infinity, that is in changing the omega from 0 to infinity. The net phase change for a minimum phase system is minimum. That is the reason we call it a minimum phase system. If you take a non-minimum phase system, it will have a phase change, net phase change, which is greater than that of the minimum phase system's phase plot, yeah. So that is why we call it a minimum phase and a non-minimum phase. So the minimum phase is only one, and there could be several other choices of non-minimum phase transfer functions. The minimum phase is that one which has all its poles and zeros on the left half plane. Even if you move one of them away, you will be having a net phase change that is greater than that of the minimum phase system, yeah. So the minimum phase system is unique, but the non-minimum phase system, of course, again it's non-unique. So there, even by looking at the phase plot, of course you have to look at the corner frequency, then you might be able to infer something, yeah, like which of the zeros is contributing like a pole to the phase, yeah. So for here, the corner frequency at A is where you would see the behavior like a pole, and the corner frequency at B here would behave like a pole, yeah. So you tally, it becomes a lot more complicated, no. You have to compare the corner frequency, the behavior at the corner frequency of the magnitude plot and the behavior at that particular corner frequency of the phase plot, yeah. At the same corner frequency, look at the behavior of the magnitude plot and the phase plot. So the magnitude plot would clearly tell you whether it's a pole or a zero, unambiguously, and the phase plot would tell you whether it's a minimum phase 0 or a non-minimum phase 0, Yeah. So that is how you can somehow identify which of these 4 transfer functions it is, right. So combining those two together with a little bit of hard work, you will be able to determine which transfer function it came from. But if it's a minimum phase transfer function, then things are very simple. You just look at the net phase change, the starting point, the low frequency asymptote and the high frequency asymptote of the phase plot. If it's n minus m pi by 2, then it's a minimum phase system, and you can then thereafter forget about the phase plot. Just look at the magnitude plot, look at the corner frequencies, and those are your poles and zeros, right. So that's why it's easier to deal with minimum phase systems when identifying systems also. So now I hope you understand why you have certain systems which are qualified as non-minimum phase systems. Yeah, so that's a point that I really wanted to sort of highlight. Okay, so now that we have understood some of these terms, we understood resonant peak, we've understood this non-minimum phase and minimum phase, why these terms are used and so on. Let us look at another term that you might encounter pretty often. Yeah, so that is something called a bandwidth. And the way I will treat this topic, this bandwidth, might not be very pleasant for you, in the sense that you might not feel very satisfied about this. Yeah, but you'll have to trust me on this a bit. So here's what the bandwidth is defined as. You see, you have a, so I mean, so far as the definition is concerned, there's nothing to be unhappy about. So for example, you have some transfer function like this, say for example, yeah, that's looking like a vertical line, it's not really supposed to be vertical, yeah, and then maybe something like this and like this, yeah. So what by bandwidth we mean that you have this, that's just the way it's defined. So you take the constant line at minus 3 dB, yeah, so you have, let's say this is the 0 dB line, so this is of course 20 log m omega, yeah, so you take the minus 3 dB line, and wherever it cuts this is what we call our bandwidth, yeah. So from 0 to this, so this omega is called our bandwidth, okay. So why is this bandwidth important? I am claiming, and this is where you might feel I am doing a bit of hand waving, but I assure you it is not the case. So I am claiming that higher bandwidth is implies and implied by faster response of a system. In fact, the bandwidth is likened to sort of analogous to the rise time, because you see there are different notions of system speed, right. One notion is, of course, you can talk about the settling time, right, we have seen in time domain. The other notion is rise time. So settling time is how soon it attains or reaches within a certain band of the steady value. On the other hand, the rise time is like how soon after the application of the input does the system start to kick up or respond to it, yeah. So that's the notion of a rise time. Now what I am claiming is that this bandwidth has a relation to the rise time. In other words, that the more the bandwidth, yeah, the smaller is the rise time, that is the faster is the system's response. So of course this is in general true, but we are not in any position to prove this for the general system. So here is where you, if you would permit me, I would do a bit of hand waving, and I would just focus on the so called second order system, okay. So suppose you have a second order transfer function like this, the underdamped case for example, okay. So suppose this is the transfer function, right. So we know that of course the asymptotic approximation of this, we are not really interested in drawing up the resonant peak to accuracy here. So suppose this is what it is, this is omega n, yeah. So now, yeah, this is it, and now you say, suppose you have, this is your, suppose this is your minus 3 dB line. Now the point is that you see, if omega n is larger, yeah, the break frequency or the corner frequency as I am calling it, the break frequency or the corner frequency shifts right, yeah, it shifts right. See the DC part, this constant gain part is just unity, yeah, you put in S is equal to 0, the DC gain, so you know that G0 is unity here, or rather let me put some K here, yeah, some K here, so it's just some K here, yeah, so this is going to be just some, this particular value here is some, okay, not this, yeah, so this particular value is here some 20 log of K, that's this value, okay. Now you see as you increase omega n, yeah, this shifts to the right, and if this shifts to the right, then for a system with larger omega n, you would have had a response like this. So you see that immediately this intersection with the minus 3 dB line also moves right, right. So therefore this increases bandwidth. Now what else do we know about omega n? Recall in the second order systems case at least, we had this, yeah, this was the constant rise time loci. This was the constant rise time loci, also the constant omega n loci, yeah. So therefore putting in these pieces together, what do we see? That as omega n increases, the rise time decreases, and as omega n increases, the bandwidth increases. So if omega n's increase is associated with increased bandwidth and omega n's increase is associated with a decreasing rise time, by relating these two, let's just put this together. So T rise is inversely proportional to omega n, and omega n is directly proportional to bandwidth, yeah. Therefore putting in these two things together, we see that T rise is inversely proportional to bandwidth. So the higher the bandwidth, the smaller is the rise time, which means that the faster the system responds. Now of course you might say, well, you've just considered the second order system, okay, and here I would make a small hand waving argument and say that, you know, all control systems like we discussed in the previous class are typically of this low pass nature. So if you just approximate it like a second order system, yeah, I know it's an abuse, because see, even for time domain systems, time domain specifications, we characterized everything with respect to the second order prototype. Yeah, we didn't go for a general higher order system and define or get its analytical expression for the rise time or the peak time or the settling time and so on. All we dealt with was second order. So here also just permit me that laxity, yeah, and allow me to just deal with the second order system. And in terms of the second order system, now I have explained to you, yeah, that this rise time decreases with an increase in the bandwidth. So basically if your user who is specifying the performance metrics, if your user is fond of time domain specifications, he or she might say I want a rise time so and so. On the other hand, if your user, and I would put it to you that you might have heard of bandwidth more often than rise time, right? You might have heard of bandwidth even before you attended this course. I am not so sure that you had actually heard of rise time before attending this course, right? So bandwidth is a more common terminology that appears in layperson's parlance. So therefore someone might give you a mix hybrid, like someone might say, okay, I want a percentage overshoot like this, but I want a bandwidth like this, and you might think, okay, this is a hybrid sort of a performance metric that's being given to me. But if you know this relation, you would immediately know, okay, if I am comfortable dealing with time domain, let me translate that bandwidth requirement to a rise time requirement, which is in a sense an omega n requirement, and then I know where to place the poles, and then you design your poles accordingly, according to whatever is being asked, using root locus technique, since that is what we have learned so far. On the other hand, if you want to design your controller in the frequency domain and someone gives you specification in terms of rise time, you immediately translate it to a bandwidth based requirement. Okay, so there are some empirical relations, I am not getting into those, yeah, you might read them up on some standard textbooks. There are some empirical relations between rise time, bandwidth, so on and so forth, right? But the central idea is that bandwidth is basically giving you the same information as rise time does. Okay, now I am going to make another sort of an explanation, and again this will be based on the assumption that we are considering a second order system. Now see, if, so I considered this k here, right? Recall I had this k here. Now okay, you might say okay, this is all well and good. So Bode plots are generally used to study this performance metric, and they are generally sketched for the open loop transfer function. But if you want to now sketch the closed loop transfer function for this case only, just allow me to do this. Yeah. So you have this k omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. Yeah, so then you have the characteristic polynomial. This is going to sit in your denominator. Of course, in the numerator you will have k omega n squared upon s squared plus 2 zeta omega n s plus omega n squared. So this is going to be a G closed loop. Yeah. Now you might say that okay, this is all open loop bandwidth. What about the closed loop behavior? Right, I might be interested in a particular choice of k, which gives me a closed loop bandwidth that satisfies certain performance metrics. Just like ultimately we have to put it in a closed loop configuration, right? That's what we've seen in root locus. So a controller and everything is generally designed with this closed loop thing in mind. So how do we do this? So now I'm going to make this again a sort of a sweeping statement. You see that a high value of k is desirable for higher bandwidth. Now one thing is for sure, if you give a high value of k here, this plot is lifted up. Yeah. So higher the value of k, the higher is bandwidth. That is obvious, no? Because if you now lift this, just like shifting this omega n to the right increased your bandwidth, now if you lift this plot here, the same plot here, yeah, the corner frequency also does not change, but now because of this lifting up, the plot also indirectly, or rather automatically also shifts a bit to the right. Yeah. So therefore the point where this minus 3 dB line intersected now has also moved to the right. So therefore this is also an observation, right? So there are two ways in which bandwidth could be increased. You can increase omega n and you can increase k. But of course all this is open loop. What about closed loop? Now in closed loop, of course, if you put this look at this transfer function now, this plant's omega n, effective omega n, will have changed. How? Look at this. Now you will have k omega n squared upon, because the denominator is common, they will cancel out, I am not writing it, so it is going to be s squared plus 2 zeta omega n s plus omega n squared into 1 plus k, right. So now your closed loop omega n CL is equal to the omega n in the open loop into square root of 1 plus k, right. So what happens if you choose a high value of k? Yeah. So up until now we have just discussed about the bandwidth of the open loop transfer function. Let me be very clear about that. And we've seen that if you have some way of designing the system's components, let's say physical components, such that omega n is increased, you'll obviously have a larger bandwidth. Similarly, if you have just a controller in the open loop configuration, and if you increase the controller's gain, yeah, it will also increase your system's bandwidth. And these are things we understand intuitively, no? Because if you are putting a k block in front of an open loop transfer function, what are you doing? You are basically saying that you are amplifying the input. So obviously the rate of rise of the input or of the output toward the application of an input is going to increase. So that helps rise time, it fits in with our understanding of this bandwidth and its relationship with rise time. But now we are saying, suppose we put it in closed loop, then also I see that in closed loop, if I am now interested in this closed loop omega n, yeah, so now I am going to, let's say this is going to be a one off, by the way. So throughout in everything that we do, we are only going to concern ourselves with open loop Bode plots. This is the only case where I am considering a Bode plot of, so a Bode plot of the closed loop system, a Bode plot of closed loop system. So a closed loop transfer function rather. Yeah, this is the one off, by the way. So don't go about thinking that this is general. Okay, in general the Bode plot is drawn for the open loop transfer function and every information is gleaned from there. Okay, so now what happens? Now notice that this transfer function, this closed loop transfer function's omega n has already shifted to the right. The higher in fact the value of k that you choose, the more it shifts to the right. Yeah. So we see that by increasing this value of k in the controller k, yeah, the closed loop transfer function's bandwidth also increases. Yeah. So it's desirable, you know, we already have this understanding, right, that if you increase the gain, the system's response becomes faster. Yeah, we have this understanding from our basic time domain ideas, right. Now we see the same understanding here reflected in this frequency domain understanding of this Bode plot, right. So we see that this closed loop systems omega n, yeah, and finally this is the claim that might be a little controversial, might appear a little controversial to you. What I am now going to say is, and let me just not write it, let me just claim it, I am going to say that the open loop systems bandwidth and the closed loop systems bandwidth are almost identical. Sounds pretty fishy, doesn't it? I mean, how on earth am I making this sort of a claim? Yeah. After all, this open loop transfer function has a different omega n, the open loop transfer function has a different DC gain, right. But now I am saying that if you just know the open loop transfer function, so basically what I am saying is that you do not have to draw this Bode plot of the closed loop transfer function. Apparently, up until now what I have told you is look at this closed loop transfer function, then this comes out to be like this, and then this omega n CL has increased because of this, and therefore we know that the bandwidth increases and so on and so forth, right. But now I am saying that eventually the way things work out, you know, whatever is the open loop system's bandwidth, the closed loop system's bandwidth will be almost the same, of course provided we are dealing with this second order business and that the value of k is pretty high. So let me explain why that is so. You see, let k is equal to 100, let k is equal to 100 and consider the second order transfer function, right. So again you might say, yeah, these are, if you go for higher order transfer function, a lot of these things do not make any sense, and I would agree, yeah, you are right, but for now we are just concerning ourselves with this sort of a numerical example, right. So then you see, let me first draw the open loop systems Bode plot. So it is something like this, let us say this is 20 log of k, yeah, and it goes like this. So suppose you have this is minus 40 dB per decade, and suppose you have this minus 3 dB line here. So this is basically your bandwidth, okay. This is the open loop systems Bode plot. Now once I have put this with the k in the closed loop configuration, then I have the overall transfer function given by k omega n squared upon s squared plus 2 zeta omega n s plus omega n into root 1 plus k times whole squared. Yeah. So now you see what is this particular systems steady gain. So this is GCL, yeah. So GCL 0 is going to be what? GCL 0 is going to be just this k upon 1 plus k, right, yeah. So for very large k, so for k, let us say they are about 100, this GCL 0 is, you know, hardly, like you can approximate this as 1, this is 100 by 101, this is almost equal to 1, right. So therefore the low frequency asymptote, yeah, so see the point is that this omega n closed loop had increased, so we had hopes that by increasing this k, whatever was the open loop bandwidth, the closed loop bandwidth would have increased because it obviously this omega n shifts to the right, but here is the crucial bit, you see the DC gain which was earlier k is now almost 0 dB, it is close to here. So if I now draw this, yeah, if I now draw this, this is going to be my low frequency asymptote for the this is going to be a low frequency asymptote for GCL, yeah. And now where is the omega n now? So let us say for example this earlier, let me take some numerical values here. So let us say this omega n is say at 10, okay, this is at 10, okay. So then where was this, where is this now omega n CL? So this omega n CL is now going to be 10 times square root 101, which is almost equal to 100, yeah. So remember it is a log scale, so it is almost close to here thereabout, yeah, somewhere here, 100. So this is where now my new break frequency is for the closed loop Bode plot, yeah. So the closed loop Bode plot's break frequency is here, and moreover, yeah, so from here it starts descending. So you might think I am deliberately drawing this close here and trying to make this picture fit, but I assure you I am not doing that. Why can you be sure that I am not tricking you here into like pictorially drawing something to make you believe something which is not true? The reason being that you see what is this value here, this is 20 log k, yeah, and then at 10 it was 20 log k, so at 100 what is this value here, yeah, what value would it have come down to now? So k is again you see 100, so this is k is 100 means this is 40, right. So this was basically equal to 40, and this can hold not just for k is equal to 100, this will hold for k is equal to 1000, wherever you take it will be then 60, right. So whatever was the value here, 1 decade hence, yeah, it has come down to, so basically at k is at omega is equal to 100, this has come down 2 decades, I mean sorry 1 decade, and at 1 decade it will descend by only 40 dBs. So therefore over here near about omega is equal to 100, yeah, this open loop transfer function has approached 0 dB, and the closed loop transfer function is also very close to 0 dB here, yeah, it is only at this omega is equal to 100 that it starts descending. So these two as if coalesce, and from hereafter they kind of follow the same plot. So the lesson to be taken home from all of this is, you might feel that by increasing this proportionality constant, this proportional gain k, yeah, maybe in the open loop transfer function you had a particular bandwidth, but in the closed loop transfer function the bandwidth will increase, yeah, because of this intuitive understanding that an increase in omega n shifts the bandwidth to the right. But notice that when you put it in the closed loop configuration, the plot also comes down. So there are two effects, you see, raising a plot increases bandwidth, similarly bringing a plot down decreases the bandwidth, moving omega n to the right increases the bandwidth, moving omega n to the left decreases the bandwidth, right. So in this case there are two things happening, one is aiding you in increasing the bandwidth, that is increase of omega n in closed loop, but the other factor unfortunately is actually sort of detrimental to your increase of bandwidth, because it is bringing the whole plot down, it is pushing the plot down, right. By pushing the plot down it is actually shifting the bandwidth back exactly almost by the same amount. So therefore barring this small aberration here, for reasonably high values of k, you will see that the open loop bandwidth is a very good approximation of the closed loop bandwidth. So that is why these are things you will encounter again, like like folklore, you will encounter that, okay, let us tell me what the bandwidth is of the open loop system. So someone prompts, oh it's 1000, and then someone says, oh, okay, so the closed loop bandwidth is also 1000, and you might don't know what, like where did that come from, yeah. So these are the reasons why those things have come into vogue, right. So I am not saying it is always going to be correct. For example, you take smaller values of k and you see that these no longer hold, but the implicit understanding is that people operate at high values of gain k, and at high values of gain k, as we have seen here, it is not a very bad assumption to make, or a bad approximation to say that the open loop bandwidth and the closed loop bandwidth of a system is almost the same, okay. So on that note we will end this particular lecture, and we will see more of the features that can be extracted from a Bode plot in the next lecture. Thank you.